This lesson we're going to start talking about inverse functions. Now we have done a little bit with inverse functions when we were working with triangles because we used the inverse sine, inverse cosine, and inverse tangent to untrig whatever it was to find a particular angle. With today's lesson, we're going to look at inverse functions graphically, and also we'll be evaluating expressions that involve inverse cosine and inverse sine. Take a look here at the graph I've shown. I'm showing y equals cosine of x, and there it is right here in black. If we said that the cosine of x is equal to 1/2, we see this blue line here. This is y is equal to 1/2. And we can locate every place on this graph where the cosine of x is equal to 1/2. So if we say something like the cosine of x is equal to 1/2, how do we know which one of these locations we're talking about? What we're going to do, though, is we're going to restrict this domain. The domain is all of the x values, and we're going to restrict it to start at 0 and end at pi. And the reason that we're doing this is because it will then generate what's called a one-to-one function, meaning that only one x value corresponds to each y value. Otherwise, we have many x values that correspond to the y value, for example, of 0.5. That graph that was shown in red, right here, that's our cosine graph between 0 and pi. So that is applying the restriction on the domain. What happens when we look at the arc cosine or the inverse cosine is we end up mirroring the graph or reflecting it over this line, y equals x. So this in blue is the entire graph of the inverse cosine. The reason that we've done this is because if you continue this graph, you might recognize that it's really the cosine graph turned on its side. And if you remember back from Algebra 1, we've got this rule here about vertical line test, and it can't be a function if it doesn't pass that vertical line test. So we get to eliminate a portion of this graph so that it is a function and it does pass the vertical line test. We call this arc cosine. Thinking about that with regard to the previous slide, we said that the cosine of some value was equal to 1/2. Or we could write the inverse cosine of 1/2 is therefore equal to that particular value. You may also see it written arc cosine. And in this case, it's equal to pi over 3. We can do the same thing looking at the sine graph. So here's sine graphed in black. In red, I'm showing the interval from negative pi over 2 to pi over 2. This is how we get that one-to-one function. I've taken and graphed that red section here, and it's graphed in blue here. So as you can see, it's still reflected over this particular line. The restriction on the domain here is from negative pi over 2 to positive pi over 2. So here are the rules regarding inverse sine and inverse cosine. Normally what we do is when we're looking at inverse functions, we actually switch x and y values and then solve for y. So in this case, to untrig the y would be the inverse cosine, would be here. So y is equal to the inverse cosine if and only if this statement here is true, that cosine of y is equal to x, and that y value absolutely must be between 0 and pi. For the inverse sine, it's the same idea. The y is equal to inverse sine of x if and only if sine of y is equal to x, and we must be within this domain. If you notice, each one of these domains cover a portion of the coordinate plane. So from 0 to pi covers here, 0 to pi. On sine, negative pi over 2 to pi over 2 goes here. In order to evaluate these expressions, there is certainly the option of using our calculator. However, oftentimes you're going to be asked for exact answers. So your calculator will only give you a decimal approximation. In order to evaluate these, you need to think about a few things. The first is the unit circle. Secondly would be all students take calculus. Third thing would be special right triangles. Finally, you would need to remember your Pythagorean identities. So, the inverse sine of 1. That means that I'm looking for the sine of what number is going to equal 1. For this, I might reference the unit circle. I remember that sine is the vertical distance. So, where is the vertical distance 1? Well, it's up at the top, which means that we're looking at 90 degrees, or pi over 2 radians. Generally speaking, your answers need to be in radians. So for this particular problem, the inverse sine of 1 is equal to pi over 2. Here again, inverse sine of 0. That's another one that I'm going to reference the unit circle. If sine is the height, where is the height equal to 0? Well, it's equal to 0 here, so the inverse sine of 0 would be 0. The next one's a little bit trickier. We're looking for the inverse sine of negative a half. So here I might rewrite this, the sine of what is equal to 1 over 2. Well, the first thing, this is negative 1 over 2. First thing I might remember would be my special right triangle. And so sine, being opposite over adjacent, is the sine of 30 degrees. 30 degrees to radians would be pi over 6 radians. However, this is 1/2, 1 over 2. I need it to be negative. So now what I'll do is look at my coordinate plane. And I remember all students take calculus. And I'm looking for a reference angle of 30 degrees where sine is negative. I know it can't be in quadrant 1 or quadrant 2. Sine is positive there. So I'm looking either at this angle or at this angle. Well, given what I know about my domain, it can only be between negative pi over 2 and pi over 2. So I'm looking for this angle, which will end up being negative pi over 6. So the inverse sine of negative 1/2 is negative pi over 6. The next one gets even harder still. I'm taking the inverse sine of a value. These don't undo each other. So the answer is not going to be 11 pi over 6. What we need to do is start with the inside of parentheses because we're using the order of operations. And I will start with my unit circle. And I know that 11 pi over 6 is going to be down in this quadrant. Why do I know that? Well, I do remember if I'm talking about sixths of pi, that this is 0 pi over 6. And as I rotate, pi over 2 is the same as 3 pi over 6. And then over here at 180 would be the same as 6 pi over 6. And this would be 9 pi over 6. And back all the way around here again would be 12 pi over 6. So I need a sixth of pi less. So this is 11 pi over 6. That means that my reference angle here is negative pi over 6. I can look at this like a reference triangle with my angle being pi over 6, which is the same as 30 degrees. So if I'm looking at a 30-degree triangle, there's my 30. Sine of that is 1/2. However, because we're still talking negatives, sine of negative 30 or negative pi over 6 will be negative 1/2. So at this point, I'll write that here, that this is actually equal to negative 1/2. So now I need to take the inverse sine of negative 1/2. That's exactly the same as the problem we did last time, and we're going back in the other direction. And when we do that, we end up with negative pi over 6. We're going to approach this problem a little bit differently because we don't really have a triangle that we use with negative 4/5. So what we're going to do instead is we're going to say that sine of some variable v is equal to negative 4/5. And this is true because the inverse sine of negative 4/5 is equal to v. What we would then say is I can take the cosine of v, and that would be equal to the square root of 1 minus sine squared of v, or in this case that would be the cosine of v is equal to the square root of 1 minus negative 4/5 squared. And I obtained this from the Pythagorean identity. So then what I find out is that the cosine of v is equal to square root of 1 minus 16/25. So that is 25/25 minus 16/25 is 9/25, which gives us positive or negative 3/5. Now, because the sign of this value is negative 4/5, it's a negative number, that means we've got to be in quadrant 4. So our answer is equal to negative 3/5.